So hello everyone. So welcome to week 8 of engineering hydrologic live interactive session. So in this week we are going to begin with a new module called as hydrological analysis. So in this module we are going to talk about like how the rainfall is getting converted into runoff, and we'll understand what is the process behind this translation of rainfall into runoff. Also we'll look into hydrograph, like what is hydrograph, what is unit hydrograph, and what is S-curve hydrograph. So in today's week we are going to cover this topic. So let us start with the very basic what we have covered so far. So in so far what we have covered is we have covered atmospheric water, we have covered subsurface water, and also we have covered surface water, right? So we know like whenever a rainfall is falling onto a surface, what are the process it has to go through before actually we get the runoff. So if we look here, like whenever a rainfall is occurring, water has to go through various processes. The first process that water has to go through is initial abstraction, which is a loss, right? So there are losses, and those losses are in form of two things. The first is initial abstraction and second is infiltration. And after this losses have been done, whatever water is left, that is converted into subsurface flow and surface flow, right? After infiltration, whatever water is left, that goes to subsurface flow, and above the surface whatever water is flowing, it's called a surface flow, right? So what we are going to see in today's week is more precisely we are going to see this process of translation of rainfall into runoff, which is a dynamic process. And why we are saying it is a dynamic process? Because rainfall and runoff both are having function of time. It changes with respect to time, right? So we are calling it as a dynamic process. So the important thing here to understand the rainfall runoff process is to understand the hydrological system concept. So if you look at if we want to talk about hydrologic system, first we should understand what is the system. So if we want to understand the system consists of three parts, right? The first part that a system consists is called as the input to the system. So if we are talking about system, the first thing that we should understand is So if you are talking about system, the first thing we need to understand is the first thing we need to understand is the system consists of three parts, and those three parts are: first is input to the system, second is we call it as an operator on which thing the system is operating. So second part is called as operator and the third is output from the system. So any system will comprise of this three part: input, operator and output. So but here we are talking about hydrological system or hydrologic system. So hydrological system will also comprise of the three part, that is input, operator and output. But here the important thing to understand is that the input and output should be a hydrological variable. So if in any system the input and output both are a hydrological variable, we call that system as a hydrological system. So in for example we can say that the input will be rainfall, which is a hydrological variable. So this rainfall is an input to the system. Here the operator would be the catchment or the basin on which the rainfall is occurring, right? And all the catchment will have a outlet points, right? So from that outlet point what we'll get is runoff. So this entire system is called it as hydrological system because the input is a hydrological variable, that is rainfall, and output is also a hydrological variable, which is runoff. So this is like the basic definition of hydrological system. Now to understand hydrological system we need to develop a model, right? And there are many models that are available, right? The model can be physical model, or it can be empirical model, or it can be a conceptual model. So there are various categories of model, right? So this we have covered in the very first week of the lecture of the subject, like what are different types of models that are available. So what we are going to study here is, we are going to study like what are the different types of model. So we can categorize that as physical model, right? It can be empirical model, or it can be conceptual model. So these are different categories of model. We know every model, like what physical model has it. Like physical models are those models which are basically run on the governing equation, right? Empirical models are those models which we have, where we will derive a relation between the input and output variable. So let us study about like what are the different types of hydrological models. So if you want to categorize, the models are those that are based on three functions. First, it can be categorized based on the space. So any model can be a function of space, or it can be a function of time, or it can be a function of randomness, right? So we'll categorize this model based on three functions, that is space, time and randomness. So let us take the first parameter. Let us consider randomness. So if we are considering any model which is having a function of randomness, then we can categorize those models as, if they are function of randomness, then we can categorize those models as either deterministic models, or either stochastic model. So based on the function of randomness, we can categorize the models as deterministic or stochastic. Now let us see what is deterministic and stochastic. So in deterministic model, we can say that it is a model which uses the law of physics, that is the governing equations, that is conservation of mass, conservation of momentum and conservation of energy, but at the same time it ignores the uncertainty that are present, right? So it will ignore the uncertainties. By this we mean that, let us say we have a model which is y is equals to mx plus c. So for each input it will give a predefined output, so it is ignoring the uncertainties. But when we talk about stochastic model, there will be some uncertainties with the output, right? So here they are considering the uncertainty. So we can say that the equation would be mx plus c plus some function of randomness, right? So here we'll get for each input will get output, but here there will be some randomness associated with the result. So this kind of models are called stochastic, this kind of models are called deterministic. They both are function of randomness. Now let us say we want to consider function with respect to some model which are having function of space, right? So those models can be divided as lumped model or distributed model, right? So based on the function of space, the models can be categorized as lumped model or distributed model. So now let us say, like, what does lumped model do and what does distributed model do? So lumped means they are ignoring the spatial variation. So what does it mean by ignoring the spatial variation? Let us say we have a catchment and we have rainfall data for that catchment. So we know that the rainfall is having spatial as well as temporal variation associated to it, right? But what does lumped model do? It will ignore the spatial variation. So what does it do? That for the entire catchment area, it is saying that the rainfall is constant throughout the catchment, which can't be true, right? So it is ignoring the spatial variation. So lumped model is ignoring that spatial variation in the data set. Whereas distributed model, it considers the spatial variation. Right? So based on randomness, we can divide a model, classify model as deterministic or stochastic. Based on function of space, we can categorize them as lumped and distributed. Now the last is based on the function of time. So based on the function of time, we can categorize the model as steady model or unsteady model, right? So by steady model, we know that it ignores the variation. It ignores variation with respect to time. It means the parameter won't change with respect to time. So that is what we mean by steady. And by unsteady means it considers variation, or it varies with respect to time. So based on these three functions, we can categorize the model as deterministic stochastic based on randomness associated. Now based on the function of space, we can categorize the model as lumped or distributed, and based on the function of time, we can categorize them as steady or unsteady model. Now that we have classified and we understood like what are the different types of model, now the important thing here to realize is to understand that is we should talk about more about the transfer function, or we call it as operator. Now this rainfall runoff process is based on linear system, right? So by linear system means we should consider the linearity in the transfer or function operator. So let us say we are considering this first function as constant. So we are keeping the transfer function as constant transfer function. So what does this mean by constant transfer function? So by constant transfer function, we mean that there is some relation between input and output of the data, right? So we can say that C times of input, which is a function of t, is equals to q of t, right? So from here we can get the constant transfer function as qt by I of t. So if you want to look at the graph also, we can say that this is the inflow, this is the outflow, and there is a linear relationship which is given by C. But this is not the case always, right? There could be some relation, we call it as differential transfer function. We call it as differential transfer function. So by differential transfer function, what do we mean by that? We know that the continuity equation is nothing but ds by dt is equals to qt minus it, right? So this is the continuity equation that we know. But also we know that the storage, that is a function of outflow, right? So storage is a function of outflow. So if we differentiate this with respect to time, we'll get an equation of ds by dt is equals to k dq by dt. Let us say this equation is 1. And also we can also write this as inflow minus outflow. So now what we are going to do, we are going to substitute this equation 1 in equation 2. So what we will get is k dq by dt is equals to I of t minus q of t, right? Now we'll keep the discharge term, that is the outlet term, on the same side. So dq by dt plus q of t is equals to it, right? Now what we can do is we can write capital D is equals to d of dt. So this term will become q of dq, right, plus q of t equals to it. So if we want to again modify this equation, what we can do, we can take kd plus 1 into qt equals to it, and from here we can get qt is equals to 1 upon kd plus 1 of it, right? So from here we can say that this term, which is nothing but it is a differential transfer function, which is a differential transfer function, right? So the relationship between outflow and inflow can be due to a constant transfer function, or it could be due to a differential transfer function. So from this we can say that the output and input is, or the rainfall runoff model is a linear system. Now how does a linear system work? So the next thing that we should understand is how does a linear system would work. So let us see here, like what are the two principles on which the linear system is working. So the linear system is based basically on two principles. So the first principle is principle of proportionality, and the second principle is principle of superposition. Now let us understand like what is the principle of proportionality and what is the principle of superposition. So first we are going to understand principle of proportionality. So the principle of proportionality states that if a solution of f of q is multiplied by a constant, right? So it is saying that if a solution of f of q is multiplied by a constant c, then resulting function, that is c times of f of q, is also a solution. So they are saying that if we have a solution, let us call it as f of q, right? And if we are multiplying this solution with a constant c, so the next result that would be coming, that is cf of q, is also a solution of this, right? So this is what we means by principle of proportionality. So in principle of proportionality, we are going to multiply a constant with the already defined solution, and the resulting solution is also a solution to that. The next is principle of superposition. Principle of superposition. So this we have also studied before, but what does the principle of superposition means? Let us say if we have two solution, let us say f1 of q and f2 of q, then the resulting solution which is obtained by taking summation of this two solution that is f1q plus f2 of q, is also a solution. So in principle of proportionality, we multiply the the solution which we already have, we are multiplying a proportionality constant to that. And principle of superposition, whatever two solution we have, we are taking the summation of it, and the resulting function, which is the summation of the predefined two function, is also a solution. So if we have two solution, let us say we have a solution f1 of q, we have a solution f2 of q. So if we take a summation of these two solution, so the answer would be something like this. So this solution, which is summation of f1 of q plus f2 of q, is also a solution. So this is nothing but principle of superposition, right? So a linear system is based on these two principles, that is principle of proportionality and principle of superposition. Now let us understand what are the input of linear system. So the input function of a linear system there are three type of input function. So the first input function is input functions of linear system. So there are three input function of a linear system. The first is called as input impulse input, unit impulse input. So unit impulse input means like there is a unit impulse input at any which is applied instantaneously at any time t, right? So it is applied at any instantaneous time. So let us say the first type of input we have is called as unit impulse. So unit impulse means an input of unit amount applied instantaneously at any given time tau. So this is input with respect to time, this is time given by tau. So an input impulse means at any instantaneous time we apply a unit impulse. So there is a unit impulse, right? This is a unit impulse which is applied instantaneously at any given time tau. So this is unit impulse. Then there is something called as unit step. So if you want to understand unit step, this is time tau, this is input of t. So the unit step is that input that goes from 0 to 1 at time equals to 0 and then it remains constant. So it is saying that it goes from 0 when time is 0, it goes from 0 to 1. Let us say it is 1. So it will go from 0 to 1 and then it will remain constant indefinitely. So it will remain constant. So this is nothing but this kind of input function is called as unit step. So it goes from 0 to 1 when time is 0 and then it remains constant over indefinite time. And the last is, we call it as unit pulse. So unit pulse is same as in unit impulse, but unit impulse is applied at any instantaneous time, whereas unit pulse is defined for is applied for a predefined time. Let us say that time is delta t. So if we applied a unit pulse over a period of time, we call it as unit pulse. If we applied it instantaneously at any given time, we call it as impulse. So difference between impulse and pulse is that impulse is applied instantaneously, whereas pulse is applied for a given period of time. So let us say this is time tau. So here we can say that we have applied a pulse for a period of time of delta t. So we call this input as unit pulse, right? Now there is something called it as response function of linear system. So this is the input function, right? So previously we have studied that a system will consist of three parts, that is input, transfer function and output. So here we are talking about a linear system, right? So the linear system will also have three parts. The first part is input. So we have talked about input function. So the input function of a given linear system is of three types. The first is impulse, unit impulse, second is unit step, and third is unit pulse. So these are the input function of a linear system. Now what we are going to talk about is the transfer function, right? So we call it as response function. So here we are going to talk about response function. Response function of linear system. So similarly, based on the type of input, the response function will be of different type. So first we'll talk about impulse response function. So first we are going to talk about impulse response function. Impulse response function, right? So impulse response function is nothing but u times of t minus tau. Now let us say what is u times of t minus tau. So if a system receives a unit pulse at time tau, then the response of the system will be a later time t. This means that whenever we have a unit pulse as an input function in any system at a given time, then the response of the system will be after a time t. It means there is some time lag between the response. So that time lag is defined by or given by t minus tau, right? So if we want to understand this, we can understand this by a representation also. We have an input which is unit impulse, right? So unit impulse is the input, right? Then the operator is the system, and the output is nothing but u times of t minus tau, right? We can also look at this graphically also. So initially we have a unit input at a given time tau. So we have a unit impulse, right? So here u is equals to 1 at any given time tau, right? So for this input there would be some output, and that output is given by response function, right? And that response function is and that function is nothing but u times of t minus tau. So there is some time lag, so we can say that the output is starting after time tau. So here we can say that this is now. If we apply a principle of proportionality and principle of superposition to the same system, we can apply principle of proportionality. So first what we are going to do, we are going to apply principle of proportionality. So by principle of proportionality means we have to multiply the input impulse with some constant value. Let us say that constant value is 3. So what we are going to do, we are going to multiply 1 with 3, right? So now the unit impulse is of 3 because we are applying principle of proportionality to it, right? So for this 3 input, which is at a time of tau 1, there would be some output, right? And that output would be based on this impact, right? So it would be 3 times of u t minus tau. So what we have done is we have just applied principle of proportionality, right? Now we also want to apply principle of superposition. So in order to apply principle of superposition, we need minimum of 2 input. So let us say we have another input at time tau naught, and we have multiplied a constant of 2. So for this also we'll have another output, and that output would be 2u t minus tau, right? Now that we have 2 input, now we can apply principle of superposition. So by principle of superposition, we'll get one more output, right? And that would be equal to and this would be summation of 3u t minus tau plus 2u t minus tau. So what we have done here is for the impulse response function for a linear system of 1 unit, we have applied principle of position as well as principle of proportionality, right? Now here we can say that the precipitation intensity is IT, right? The intensity or the time interval is d of tau. The impulse output or impulse input is IT times of d of tau, because the precipitation is in terms of intensity. So precipitation intensity means it would be somewhere in centimeter per hour or mm per hour. So if we want to get the input, so the input is a precipitation data, right? So in order to get the impulse input, what we have to do, we have to multiply the intensity with time duration. So that is what we have done here. And the output is, or the response is, runoff, right? So how we are getting the runoff? So we are getting the runoff after certain time lag, right? So IT of u t minus tau of dt. So this is how we are getting the runoff. Here we have seen here, right? So 3 is nothing but the intensity I, and u of t minus z is nothing but the response function. Now let us say we want to get the response of complete function. So what we are going to do, so if we want to calculate q of t, so we are going to integrate this term from 0 to t. So 0 to t of IT u t minus tau of dt. So if we integrate this term, we'll get the runoff value, and this equation is very important. This is known as convolution integral. So this is a fundamental equation to solve a linear system on a continuous time scale. So based on this equation, we can derive the response function for unit step as well as for unit pulse. So if we want to see the response function for a unit time or unit step, so we can use the same equation. By using the same equation, we can derive response function for unit step. So now what is going to change here? So if you look at this equation, so if you are talking about unit step response function, so we know a unit step response function would be something like this, right? It goes from 0 to 1. So here the value of intensity, that is IT, is 1, right? So if we want to write the convolution, like using the convolution integral itself for unit step response, we can get the runoff value for unit step. So qt would be equal to 0 to t u t minus tau of dt. So this is the output equation for unit response equation. Same equation we can get for unit pulse also. So based on this same concept, we can derive output equation for unit pulse function as well. So we are going to look into unit pulse equation, unit pulse input function into more detail when we talk about unit hydrograph. So let us first talk about what is hydrograph, and then we'll talk about unit hydrograph, and when we are going to discuss unit hydrograph, we'll talk more about unit pulse function also. So let us first understand like what are the characteristic of a storm hydrograph, right? So if you are looking at this figure here, in this figure we can see that the first part AB, then there is part BC, then from C to D, D to E and E to F. So this same figure we have studied in the previous week also, right? Where we have understood like what are the characteristics of different features of storm hydrograph, right? So we know that BC is the rising limb, AB is the recession limb, rising limb, then DE is falling limb. What are the component or what are the characteristics of each of this part? But the important thing here to understand is this part. This is nothing but this is impulse, right? This is a pulse which is varying over a time of TR, right? So what does this TR? So TR is nothing but the duration of storm, right? So this is the input to the catchment having a storm duration of TR. Then we can look at the figure from point B to point E, that is from the starting of rising limb to the ending of falling limb. This time is nothing but it is called as base flow or time base, right? Then there is something called as time peak, TP. Now time peak is nothing but the time elapsed from the beginning of the rising limb to the peak discharge, right? So the time taken from the point where B is starting to the point of peak discharge is called as peak time or time to peak. And there is something called as time lag. So if you look at this figure, you know that the time lag is the maximum time taken by the water to travel through the catchment. So it is nothing but the distance between the point where the falling limb is beginning to the centroid of the duration of storm. So this time is nothing but time to or time lag or lag time, right? Now if we look at here, hydrological system can be modeled by, there are different approaches to model hydrological system. So one of the approaches by using unit hydrograph, right? So unit hydrograph, what does it does? It operates on rainfall, that is effective rainfall, and using effective rainfall, it gets rainfall, it converts into runoff. So it means for a unit hydrograph, the input is effective rainfall, right? So here we have seen a rainfall hydrograph, right? So it is the input to a unit hydrograph, and the output from a unit hydrograph is nothing but a discharge versus time curve, that is a hydrograph, which is nothing but a runoff. So input is rainfall and output is runoff for a unit hydrograph. Now let us see what is the definition of unit hydrograph. So the unit hydrograph was, this concept was proposed or given by Sherman in 1932. So it is defined as a direct runoff hydrograph resulting from 1 centimeter of excess rainfall generated uniformly over the drainage area at a constant rate of effective duration of DRs. So the important thing here is to understand that it is defined as a DRH, that is direct runoff hydrograph resulting from a 1 centimeter of excess rainfall generated uniformly over the drainage area at a constant rate of effective duration of DRs, right? So now the next thing to understand is unit hydrograph is a unit pulse response function of linear hydraulic system, right? So we know what is unit pulse response function now. So this figure we have studied previously also. So unit pulse means there is a unit input over a period of time, right? So this for a unit hydrograph is nothing but 1 centimeter of excess rainfall. So we can compare these two figures and we can understand that for a unit pulse response function of a linear hydrologic system, the unit input is a unit pulse for a period of time, right? So the same thing for unit hydrograph is 1 centimeter of rainfall over a time period of D, right? And the output is a pulse response function, but here the output is a DRH, right? So input is excess rainfall for a unit hydrograph and output is a direct runoff hydrograph, which is nothing but a pulse response function. Now there are some assumptions that are associated with unit hydrograph, right? So let us see like what are the assumptions that are associated with unit hydrograph. The assumptions of unit hydrograph. So the first assumption is that the system is linear, right? The second assumption associated is the system is time invariant. So by time invariant means it does not change with respect to time. The second is effective rainfall is uniform over catchment. This is the third assumption. The fourth assumption is that the time base remains constant. The peak might change but the time base will remain constant, and the last assumption is that the area of the catchment should be between 2 to 5,000 kilometers square. Right? So these are the assumptions that are associated with unit hydrograph. The system is linear, it is time invariant, the effective rainfall is uniform over catchment, the time base remains constant, and the area of catchment should be between 2 to 5,000 kilometer square. Now let us see like how to derive a unit hydrograph. So the three important things that you need in order to derive a unit hydrograph is, the first is the stream flow hydrograph at the outlet, the drainage area of the catchment, and the rainfall hydrograph, that is the input. Now this is nothing but a unit hydrograph that is derived from a isolated storm, right? So what are the steps in order to derive a unit hydrograph from a isolated steps? We can note down the procedure for this also. It would be easier if we look at the procedure, right? So what we are doing is we are deriving a unit hydrograph from isolated or single storm event. So what are the steps? So the first step involved is we should select a isolated storm of some duration. Let's let us say we should know the duration of that storm. So the first step is selecting a storm having desired duration D, right? So if we have a storm and we know the duration of that storm, then we can proceed with deriving a unit hydrograph for that storm. The second part is to plot Q versus time plot, that is discharge versus time curve for that storm. The third is base separation. So what we are doing here is we are separating the base flow contribution to that runoff. So why we are doing this here? This is because in order to derive unit hydrograph, we need to know the direct runoff value, right? So for that we need to separate the base flow. So there are different techniques in order to do that. We have discussed that in the prior class, in the prior week, for base separation or base flow separation. There are technique called as straight line method. Then there is variable slope method, right? Fixed base method. So there are three different techniques in order to separate the base flow from a unit hydrograph. The next step is to find the volume of DRH. Now that we have separated the base flow contribution into that catchment, we can calculate the volume of direct runoff hydrographs, right? So how we can do that? In order to calculate the volume of DRH, we can simply calculate the area under the curve. So if we calculate the area under the curve, we'll get the volume of DRH. Next we can calculate is the depth of effective rainfall. And how we can do that is by dividing the volume of DRH with the area of catchment. See, now that we know the depth of effective rainfall, what we can do is we can calculate the ordinates of DRH. So we can calculate the ordinates of unit hydrograph. And how we can do that? By dividing DRH ordinate with depth of effective rainfall. Okay, so these are the 6 steps that are involved in order to derive a unit hydrograph from an isolated storm event. Right? Isolated storm event means it is a single storm event. Now let us say there are multiple storm events. So how we can derive the ordinates of unit hydrograph? So now we are considering a case of a complex storm of duration multiple of D. So there is a standard equation which we can use in order to derive discharge for this kind of problem, which is where PM is excess rainfall depth, Qn is DRH ordinates, and U is unit hydrograph ordinates that is to be found. Right, so this is the standard equation which is used in order to derive DRH of or unit hydrograph or ordinates of unit hydrograph. Now we can see like how we can apply this to a problem. So if you look at the figure here, this is the input, right? So input is nothing but a pulse. So there are three input, P1, P2 and P3. So what we are going to do, we are going to calculate the pulse response for each input. That is, we are going to calculate the input pulse response which is applied to P1, then which is applied to P2, and then which is applied to P3, and then we are going to take the summation in order to get the final output, right? So let us see how this equation can be used in order for different pulse. So let us say we have three input pulse. So this is nothing but effective rainfall, right? So we have three input pulse, that is P1, we have P2 and we have P3, right? So these are three input pulse. So for each input pulse we'll have the input response, right? The response function. So for P1, the response function will start from P1, right? And it will goes something like this, right? This will be U1, then it will be U2, then it will be U3, U4, U5 and U6, right? So this is the response function of applied to P1. This is the response function which is applied to P1. Now let us calculate the response function which would be applied to P2. So there will be some time lag. So that time lag will be of this one. So the response function will start from U2. That is from P2. So the response function will be, this will be U1, U2, U3, U4, U5 and U6. So this will be U1 now. This will be U2, U3, U4, U5 and then it will be U6. Right, so this is U6 and this is applied to P2. So similarly it would be applied to U3 also, right? So when it is applying to U3, this will be U1, U2, U3, U4, U5 and U6. Right, so this is the response function that is applied to pulse, input pulse 3. Now what we are going to do, we are going to add the response function, right, to get the output. So this is the output Q. So the first input function would be here, that is starting at P1. This is called U1 times of P1 because here it is U1 and here it is P1. So this is U1 times of P1, that is P1 U1, right? So this is for first function. Then it will be P1 U2, then it will be P1 U3, P1 U4, P1 U5, and then it will be P1 U6. So this is the output because of first impulse and first output response function, right? So P1 U1. The next would be because of P2 U2, right? So it will start from here. Then similarly for third. So third one, it will start from here. Right. So if we want to find the output for individual response function, that is we want to find Q1. So Q1 is nothing but product of P1 and U1. If we want to find Q2, so Q1 will be because of P2 U1 plus P1 U2, and similarly Q3 will be because of P3 U1 plus P2 U2 plus P1 U3. So if we want to generalize this equation, that generalized equation is nothing but this equation. So in this way we can derive DRH from a unit hydrograph, right? Now let us see what is S hydrograph. We have studied like what is unit hydrograph. So in unit hydrograph, the important thing to understand is that it is resulting from 1 centimeter excess rainfall which is occurring uniformly over the catchment, having a uniform R, like for an effective R, that is dr. So S hydrograph is nothing but S hydrograph is defined as a DRH observed at the outlet of catchment when it is subjected to effective rainfall intensity of 1 by d centimeter per hour. So the important thing here to understand is that it is subjected to an effective rainfall intensity, whereas unit hydrograph was subjected to an effective of unit excess rainfall, right? Here it is because of unit rainfall intensity of 1 by d centimeter per hour. Also the important thing to understand here is the unit hydrograph was based on a unit pulse response function, right? Whereas S hydrograph is based on unit step response function. Now let us see like how to obtain S hydrograph or S curve. So it is based on a complex storm, like it is having a complex storm of multiple storm event, right? So it is having an infinite number of effective rainfall pulses having dr duration each. Here in the figure we can see that whereas in unit hydrograph there was only one input when we are talking about single storm duration event, whereas for S hydrograph there are multiple number of effective rainfall pulses having dr duration, and the combined response is represented by the combined response of this input is given by S hydrograph, right? So how we can obtain this? So can be obtained by summing the ordinate of series of dr unit hydrographs spaced at dr apart. So what we are going to do for this input pulse, will calculate the output first. So that output is nothing but u times of t. So for second it would be u times of t minus d. There would be some time lag and then it will remain same, but there would be some time lag associated with it. Then the important thing here is in S hydrograph there will be some equilibrium discharge, which is the maximum rate of direct runoff. What is this equilibrium discharge? We'll study here in the next part. And also in order to calculate S hydrograph, we required number of unit hydrograph, and those number of unit hydrograph can be obtained by this term time base by d. So if we know the time duration, like the dr from storm for the each storm duration for each storm event, and we know the time base, right? So that dividing the time base to the duration, we can calculate the number of unit hydrograph that are required. So let's talk about equilibrium discharge here. So in order to represent the rainfall volume due to 1 centimeter of excess rainfall divided by the duration of R, we can calculate equilibrium discharge of S hydrograph. So that is nothing but 1 by D of area. So this 1 by D is nothing but centimeter per R and area is in kilometer square. So we want to convert this into the unit of discharge, which is meter cube per second. So we can convert this centimeter into meter, that is 10 to the power of minus 2. This area, which is in kilometer square, we can convert this into meter square by 10 to the power 6. So the numerator is in meter square, meter cube now. And R we can convert into seconds, that is 60 by 60. So if we convert this, we'll get the equation of discharge, which is meter cube per second. And the formula of equilibrium discharge will come up to be QS is nothing but 2.77 of 8 multiplied by area and divided by time, right? Duration of storm. So we should keep in mind here is, if we want to use this equation directly, the area should be in meter square and time should be in second. Then we can apply this equation directly, or else we have to go with the standard equation, that is area divided by duration of time. If the time duration is intensity is in centimeter per hour and area is in kilometer square, right? So this is all about equilibrium discharge of S hydrograph. So I think so far we have covered all the theory that has been there in this week's sessions. Now let us go and solve few example based on the theory that we have studied. So first we'll see the first example, which is a simple example based on drainage area. So here in this example they are asking us to determine the drainage area at the outlet of the catchment, which has produced a triangular unit hydrograph having a time base of 16 hours and peak discharge of 28 meter cube per second. So in order to solve this numerical, we have to be thorough with the procedure of determining DRH, right? So what is the what is the procedure? In order to calculate the volume of DRH, we need to calculate the area under the curve. So here they are saying that area is a triangular unit having base of 16 R and peak discharge of 28, right? So they are saying that the base is 16 and height is 28. So if we calculate the area of this triangle, we can get the volume of DRH. But they are asking us is to calculate the drainage area. So how we can do that? Since we know that the volume is, we can divide this volume with the excessive rainfall of unit hydrograph, that is 1 centimeter. So if we divide this volume by 1 centimeter, we will get the area. So let us solve this problem. So they are saying that time is 16 hours and peak discharge, that is QP, is 28 meter cube per second. Right, so we know this two values. So what we can do is we can calculate volume of DRH, and volume of DRH is nothing but area under the curve. And this area under the curve, they are saying that the area is triangular. So for triangular, the area is half into peak discharge into time. But the condition is that the time should be in seconds, right? So half into peak discharge is 28, 16 R we can convert into seconds. So if we multiply this term, we'll get the volume of DRH, right, which will be in meter cube. Now the next thing is to calculate, they have asked us to calculate the area, actual area of the catchment. So how we can do that? Since we know the volume, we can calculate the depth of ER. So there is another formula of depth of ER, which is equals to volume of DRH divided by catchment area, right? But in this problem they have asked us to calculate catchment area, and depth of ER for unit hydrograph is 1 centimeter, that is 1 into 10 to the power of minus 2, and volume of DRH is known to us, so the only term that is unknown is catchment area. So we can calculate catchment area equals to, so this is a very simple problem. We can see the solution also. So see, first they have calculated the runoff volume or volume of DRH, which is 8066400 meter cube. Now since we know this volume, we can simply divide it by excess rainfall and we can get the value of area. So they have divided here. So they have calculated the area also. So the area comes up to be 8.64 10 to the power 6 of meter square. So this is very simple problem. Just we need to be very clear like how what are the steps to calculate the DRH of unit hydrograph. Now next question they are asking is the derivation of unit hydrograph. So they are asking us to derive a unit hydrograph. So they are saying that derive the unit hydrograph for a drainage basin of 175 km square from the observed total runoff hydrograph given below. So they have given the runoff hydrograph value here. Also they have given the rainfall hydrograph ordinates. Determine the duration of hydrograph. So here they have asked us to determine the duration of hydrograph. It means whether the duration is 2 hours, whether the duration is 4 hours or 6 hours, that we need to derive. So how we can do that here is, since they have given us the discharge value and they have given us the input, right? So we need to calculate, first thing is to calculate DRH. So how we can calculate DRH from unit hydrograph is by first we need to separate the base flow. So first thing we should do is we should first look at the given data and we should calculate the base flow. So if you look at this data set, we can say that the value of 12 meter cube per second is repeating here, like it is 12 for time of 6 hours and again after 48 hours it is 12. So we can say that this 12 is nothing but it could be a base flow. It could be because of the base flow, right? So what we can do is first step is to calculate the DRH from the given data set. So in order to know the DRH, we need to know the base flow. So here what we are going to do is we are going to take base flow as 12 and then we are going to subtract this base flow from the given data. Then we'll get the value of DRH. So here we can see this is stream flow data and then they have calculated direct runoff. So how they have calculated direct runoff? They have taken 12 as the base flow, right? So they have subtracted 12 from 12, they got 0. Then we have subtracted 120 from 12, we got direct runoff as 108. So similarly, we have subtracted value of 20 from each stream flow in order to get direct runoff hydrograph. So now that we know the ordinates of direct runoff hydrograph, the next thing is to calculate the depth. If we know the effective depth, then we'll divide the effective depth with direct runoff hydrograph to know the ordinate, right? We know the steps now, right? So first step was to separate the base flow. So we have separated the base flow and we got the value of DRH. Now the next step is to calculate the effective depth. Since we know the volume, now we can calculate the volume. How we can calculate the volume? We know the peak value, like we know the total value. So the total value is 1705 meter cube per second. So this value we are going to multiply with the duration. So the duration is 2 hours. So 2 hours means 2 into 60 into 60. So we got the volume of direct runoff. And also we know the value of drainage area. So we know the volume, we know the area. So we can get the value of excess depth of excess runoff. So we got the value of depth of excess runoff, which is 7. Right? So we got the value of excess runoff, which is 7 centimeter. So now what is the next step? The next step is to calculate the ordinates. How can we get the ordinates of unit hydrograph? By dividing this value of 7 with the direct runoff. So 1708, which is in meter cube per second, divided by 0.07. Sorry, divided by 7.01. So we got the value of 15. Similarly, 228 divided by 7, we got the value of 32. So similarly, we are getting the ordinates of unit hydrograph, right? Now the next step is to calculate to plot rainfall hydrograph. So in order to plot rainfall hydrograph, what we need rainfall intensity. So what we have done here is we have divided the depth of rainfall with the time duration. So 1 divided by 2, 0.5, 0.5 divided by 2, 0.5, because the time duration is 2. So we'll divide each rainfall depth with 2. We'll get the rainfall intensity. So we have plotted this rainfall hydrograph. Now what we need to do is we need to assume the value of phi such that the estimated runoff is equals to the depth of runoff, right? It means the excessive rainfall value, that is the input, should be equal to the output, which is the depth of runoff. So if the input and output is matching, we can say that the phi value is, whatever phi value we are assuming, is constant. Why we are doing this is because based on the value of phi we can separate the DRH value. We know that, we have studied this in previous week also. So firstly we have assumed phi value equals to 1 and we got the estimated runoff equals to 10.5, which is not true because the depth of direct runoff which we got was 7.01. So again we are going to assume new value. So that new value which we assumed was 1.5 and the estimated runoff that we got was 8. So again it is not true. So what we can do is we can simply take the output result as 7.01 and we can get the value of phi. So that value which we got of phi is 1.75 centimeter. Now based on this value we can calculate like what is the time duration. How we can do that? Here in the figure we can say that the rainfall hydrograph, the value of phi index is 1.75. So if the value of phi index is 1.75, only those rainfall intensity will be taken whose value is greater than 1.75. So there are how many rainfall intensity values which are greater than 1.75? It is 2. There are only 2 values, that is 3.25 and 3.75. So only these 2 impulse will be active, that is of time duration of 8 hours and 10 hours. It means 2 hours of this and 2 hours of this. It means total of 4 hours will be active. So from this we can say that the unit hydrograph which we have derived here, this value, the unit hydrograph which we have derived here is for how many hours? It is for 4 hours. And why it is for 4 hours? Because when the value of phi is 1.75, only 2 pulses are active, that is of 3.25 and 3.75. So 2 hours of this and 2 hours of this, which is 4 hours. So that's why we can say that the unit hydrograph that we have derived here is of 4-hour unit hydrograph, right? So this was a problem which was based on how to derive unit hydrograph. Now the next problem is for derivation of DRH. It means they have given us unit hydrograph and from unit hydrograph we have to derive DRH. So what we are going to do here is, firstly we have plotted the unit hydrograph based on the given value. So this blue plot, light blue color plot, it shows the unit hydrograph. Now we want to derive DRH due to excess rainfall of 2 centimeter, right? So what we can do that, in when we want to find a unit hydrograph ordinate, we divide it by excess rainfall, right? We know this equation, DRH is equals to unit hydrograph into excess rainfall, right? The relationship here is, if we want to find the ordinates of unit hydrograph, we need to divide DRH ordinate with respect to excess rainfall. So we know this. So now what we are going to do, we have given ordinates of unit hydrograph and we have been given excess rainfall and they have asked us to calculate DRH. So we are going to use this equation. So we are going to simply multiply excess rainfall value with unit hydrograph ordinates. So the first value was 2, 0, 0 into 2 is 0, 10 into 2 is 20, 16 into 2 120, 120 into 240. Now then they are saying is there is a time lag of 3 hours and we want to calculate DRH due to excess rainfall of 3 centimeter. So what we are going to do, first similarly we are going to obtain another table of DRH due to excess rainfall of 3 centimeter. It means we'll get another column here which will give us value of 0, then 10 into 330, 60 into 3 180, 120 into 360, 80 into 3 240. But since there is a time lag of 3 hours, we are going to shift it into 3 hour value. So that's the reason we are shifted here, because there is a time lag of 3 hours. So we have multiplied this column with 3, column second with 3, and then we have taken a time lag of 3 hours, so we have shifted it into by 3 hour time lag. Now they have asked us to find a combined DRH. So combined DRH means we have to apply principle of superposition, then it means we just need to add this value. So 20 into plus 0, 20, 120 plus 30, 150, and that is combined DRH. So here we have plotted first unit hydrograph. For that same thing we have plotted 2 hours, 2 centimeter DRH. Then this purple line shows 3 centimeter DRH, which is having a time lag of 3 hours. So it has been shifted by 3 hours. And the red curve indicates combined DRH. So this is also a very simple problem. Now I have also given few problems which would help us to practice this kind of numericals. So first we'll look into first problem. So here they are saying a effective rainfall of 10 centimeter is occurring over a catchment. An effective rainfall of 10 centimeter over a catchment produces a peak rain runoff of 50 meter cube per second, 500 meter cube per second. Over the same watershed, another 5-hour effective rainfall of 3 centimeter produces a peak flow of what? So they are saying that when the rainfall of 10 centimeter is occurring, the runoff is 500 meter cube. Now they are saying when the effective rainfall is reduced to 3 centimeter, what would be the peak flow? So we know that if the effective rainfall is reducing, it means the peak will also be reduced. So biologically we say that when 10 centimeter of rainfall was occurring, the peak flow was 500. So in the same catchment for same effective hour rainfall duration, if 3 centimeter of rainfall is occurring, the peak flow would be less than 500 meter cube per second. So now let us calculate. Now how we can calculate that is, so they have given us effective rainfall here, that is effective rainfall is 10 centimeter, and also they have given us the value of peak flow as 500 meter cube per second. Then they are saying when the effective rainfall reduces to 3 centimeter, what would be the peak flow? Right, so this is the condition that we have. They are saying that the effective rainfall is 10 centimeter, which is occurring for 5 hours, right? And the peak discharge that was observed was 500 meter cube per second. Now if the duration is same but the effective rainfall is reduced to 3 centimeter, what is the peak discharge? So first what we can do is we can calculate the unit R P coordinate. So if we know the unit R P coordinate, then we can just simply multiply it with the excess rainfall of 3 centimeter and we can get the peak discharge. Why? Because the unit hydrograph P coordinate will be same. So how we can do that? This is DRH P coordinate, right? And this is excess rainfall. So we know the relation that UH ordinate is nothing but DRH ordinate divided by ER. So we can simply divide this 500 divided by 10 and we can get the value of 50. So the unit hydrograph P coordinate is 50 meter cube per second. Now what we can do, we can use the same equation and we can calculate DRH by changing ER as 3 and unit hydrograph as 50. Right, so we can write DRH is equals to UH into ER. So we know UH is 50 and effective rainfall that they have asked is 3. So we can say that the DRH is 150. Right? So the important thing here to remember is that whenever the excess rainfall is reducing, we know that the DRH will also reduce. So initially when excess rainfall was 10 centimeter, DRH was 200. But when excess rainfall got reduced to 3, the DRH also got reduced to 150. Now let us see next equation. The next equation is based on S-curve hydrograph. So they are asking us to find is equilibrium discharge for S-curve hydrograph in meter cube per second obtained from a 4-hour unit hydrograph and the catchment of 320 kilometer square. So the area is 320 kilometer square and the time duration is 4 hours, right? And they are asking us to calculate is equilibrium discharge, that is Q equilibrium, right? So we know Q equilibrium is nothing but A by D, right? But we need to convert area into meter square and R into second. So area is 320, so we are going to convert it into meter square, right? So duration is 3 hours. So we are going to convert 3 hours into seconds. So it would be 4 hours. So 4 into 60 into 60. Right? So now we can solve this equation and we can get the value of Q equilibrium. So this is also a very simple problem. You just need to do the unit conversion and you have to remember the Q equilibrium. The next equation, the next numerical is, they have given us 6-hour unit hydrograph of a catchment having area 1500 km square, and it is approximately as a triangular unit hydrograph with a base period of 10 days. The peak flow in the DRH of this basin is produced by ER of 5 cm is equal to how much? So they are asking us to calculate the peak flow, right? So how we can do that? So again we need to remember the procedure how to derive the DRH, right? So firstly what we are going to do is we are going to calculate the volume, right? So volume is nothing but area under the curve. So area is nothing but half into QP into time of base, right? So volume is nothing but area under the curve, and that area they are said is to be triangular. So for that triangular, the base is TB and peak discharge is QP. So half into QP is equal to time base. So the base time they said is of 10 days, right? So 10 days means 10 into 24 into 60 into 60, right? So we are converting days into seconds. So this is the value of volume, and we don't know the value of QP. Now this volume, if we derive this volume with the area of catchment, we'll get the value of excess rainfall, right? So we know excess rainfall, the depth of excess rainfall is equals to volume divided by catchment area. So excess rainfall that they have given us is 5 centimeter, right? So 5 centimeter excess rainfall they have given, and volume is that we have calculated. Right? Now the value of catchment is also known to us, catchment area, which is 1500 kilometer square. So we have converted into meter square. So if we solve this equation, we will get the value of Q peak, which they have asked us to calculate, which will be in meter cube per second, right? Now let us see another problem, or the last problem. So here in this problem they are saying that the peak of flood hydrograph due to a 3-hour duration is isolated storm in a catchment is 270 meter cube per second. So they have given the duration of storm, and also they have mentioned the catchment area. They have also mentioned the peak of that storm, that is 270. The total depth of rainfall is 5 centimeter. Assuming an average infiltration loss of 0.3 centimeter per hour and a constant base flow of 20 meter cube per second, estimate the peak of 3-hour unit hydrograph. So first thing that they have asked is the first thing that is given to us is duration of rainfall. So the duration is known to us. So that duration is 3 hours, right? Then they have mentioned losses. So that losses are nothing but 0.3 centimeter per hour. So 0.3 centimeter per hour means we have hour of 3 duration. So the losses would be account of 0.9 centimeter. For 1 hour the losses is of 0.3 centimeter. So for 3 hour it would be 0.3 into 3, which is 0.9 centimeter. Then they have mentioned us is total depth. So the total depth is 5.9. But what we need is, we need excess rainfall, right? So So what is excess rainfall? Excess rainfall is nothing but the total depth of rainfall minus the losses. So total depth of rainfall is 5.9 minus losses is 5 centimeter. So the value of excess rainfall for that storm duration of 3 hours is 5 centimeter. Also they have given us is the peak flow of hydrograph, that is 270 meter cube per second, right? So this is the peak flow of hydrograph, but we need the peak of DRH. So how we can calculate the peak of DRH? They have given us the base flow value. So base flow is 20 meter cube per second. So if we separate the base flow from the value of storm hydrograph, we can get the value of direct runoff hydrograph. So the value of peak of DRH would be 270 minus 20, which will be 250 meter cube per second. Now in the equation they are asking us is to find the peak of 3R unit hydrograph, right? So the first thing that they have asked is to calculate, peak of unit hydrograph, right? And the second thing that they have asked is to find base of 3R unit hydrograph. So these are the two unknowns that they have asked us to calculate. So how we can do that? We know this relation. In order to calculate ordinate of UH, that is unit hydrograph, we need to divide the ordinate of DRH with respect to excess rainfall, right? So here we have required to calculate peak of unit hydrograph, and we know the value of peak of DRH, and also we know the value of excess rainfall. So what we are going to do is we are just going to divide peak of DRH with excess rainfall. So peak of DRH is 250, excess rainfall is 5. It means peak of unit hydrograph would be 50 meter cube per second. So this is the first unknown that they have asked. Now the second unknown that they have asked is to calculate the width. So in order to calculate the width, we need to calculate the volume, right? So first we will calculate the volume. So we know this, that excess rainfall of unit hydrograph is equals to volume of unit hydrograph divided by catchment area, right? So excess rainfall of unit hydrograph is nothing but 1 centimeter, that is 1 to the power of 10 to the power of minus 2. We want to calculate the volume of unit hydrograph. So that volume of unit hydrograph is nothing but half into peak of unit hydrograph, which is 50, into base. So base is unknown to us, but it would be in hours, so we are going to convert that into seconds. So this is the unknown term, and they have also given us the catchment area. So the catchment area that they have given is 567 kilometer square. So we have converted that into meter square, right? So if we solve this equation now, we'll get the value of time base, that is, it would be 63 hours. So these are like the few examples that can help us to solve numericals based on this concept, right? So in today's class we started talking about hydrologic analysis. So we talk about like what is the hydrological system. So any system that consists of input and output variables as hydrological variables are called as hydrological system, right? And we know that this hydrological system is a linear system. Then we also talk about different classification of hydrological models. So hydrological models are based or classified based on the functions, 3 functions. The first is function of space, function of time, and randomness. So when we account for randomness, so based on the function of randomness, a model could be deterministic or stochastic. Like, so the deterministic models are those models which consider that ignores uncertainty, and the stochastic models are those that considers uncertainty, right? Then we have divided the model based on function of space. So based on the function of space, model could be lumped model or distributed model, right? So lumped model are those model which ignores spatial variation. Distributed model are those that accounts spatial variation. Then based on the function of time, a model could be steady or unsteady. Steady ignores variation with time, unsteady varies with time, right? So we have studied the different classification of hydrological model also. Then we talked about hydrological system, right? So if we look at this figure, the red color pointed shows the watershed divide, that is the watershed boundary. Then this surface are nothing but watershed surface. Then this boundary is the system boundary that we have considered. Then the input is the precipitation and the output is the stream flow. So from this function we can say that the output is a function of storage, right? So we know that storage is directly proportional to the output, so storage is equals to K times of Q. So this type of approach is nothing but it is example of linear reservoir. So then we started talking about more of linear reservoir. Then we talked about the transfer function. So the transfer function could be a constant transfer function or it could be a differential transfer function. Then we talked about more on linear system. So linear system are based on two principle, that is principle of proportionality, where what we do is we just multiply the solution with a constant value, and that value is also a solution of the linear system. It means principle of proportionality, we just multiply the result with a constant value. In principle of superposition, let us say if there are two output with us, right, f1 of q and f2 of q. So if we add this two output, there would be a new output which is also a solution of the system. So these are the two principles of linear system. Then we talked about the input function of linear system. So the input function could be of three type. It could be a unit impulse which is applied instantly at any time tau. Then there is unit step function which varies from 0 to 1 at time equals to 0. Then it remains constant over the period of time. This is called as unit step. And then there is unit pulse. So unit pulse is nothing but it is a input of unit amount which is occurring over a defined period of time, that is delta t. Then we talked about the response function of linear system. So considering the case of impulse input, we have derived a generalized equation which is known as convolution integral, and based on the convolution integral we have derived the response function for unit step and unit pulse as well, right? So we have derived this equation of convolution integral, which is this equation qt is equals to 0 to t I times of tau ut minus tau dt. So this is convolution integral. So we can use this same equation for unit step response function as well as for pulse response function. Then we talked about unit hydrograph, right? So we talked about the unit hydrograph, which is nothing but it is resulting from 1 centimeter of excess rainfall which is generated uniformly over the rained area at a constant rate for an effective duration of dr. So we know that the unit hydrograph is nothing but it is a unit pulse response function of linear hydrologic system. So this is nothing but a representation of unit pulse response function, where unit input is a unit pulse and output is nothing but a pulse response function of ht. Similarly, this is applied to a unit hydrograph where input is a ER, that is excess rainfall, and output is nothing but DRH, right? Then we have talked about assumptions in hydrograph, that is it is linear, it is time invariance, then excessive rainfall remains constant over the period of time, then the area of catchment should be between 2 to 5000 km per square. Then we talked about that the DRH response from catchment represent unchanging characteristics of the catchment, so we should consider the changing characteristics and then we have to derive the DRH. Then we looked into the procedure like how to derive unit hydrograph. So there are certain steps. The first step is to separate the base flow. Once you have separated the base flow, you get the value of DRH. Then you can calculate the volume of DRH by taking the area under the curve, and then you can calculate the depth of excessive rainfall by dividing the volume of DRH divided by the catchment of area, and then you can calculate the ordinate of unit hydrograph by dividing the ordinate of DRH with respect to the excess rainfall depth, right? Now we have also looked into this thing, like this is nothing but it is how we can derive the DRH from multiple storm events, right? So we have also looked into a standard equation, this equation which is known as discrete convolution equation. This equation can be used to derive the output when there are multiple storm events, right? Then we talked about S hydrograph. S hydrograph is nothing but when DRH is observed at the outlet of a catchment when it is subjected to effective rainfall intensity of 1 by d centimeter per hour for an effective period, right? So similarly, as unit hydrograph is based on unit pulse response function, S hydrograph is based on unit step response function, right? So we have also talked about how S hydrograph is plotted and how it can be obtained. Then we talked about various numerical. The first numerical was simply based on to calculate the drainage area of a catchment. Then we saw like how we can derive unit hydrograph. Then we also saw numerical based on derivation of DRH, like how to derive a DRH when we have the value of unit hydrograph. And then we have solved four different example, where we have also taken an example based on equilibrium discharge for S curve obtained from a 4-hour unit hydrograph. So we know how can we can calculate the equilibrium discharge, right? So we have taken, like we have covered everything. So in the next class I think we'll talk more about different hydrographs that are available. We'll talk about synthetic unit hydrograph, we'll talk about instantaneous hydrograph. So this is so far for today's class. So we have started with a new module which is called as hydrologic analysis, which is module 5. So the same module will be covering in next week's session, that is week 9. Again we'll talk about more into hydrological analysis, and then in the next session we'll start with another topic, that is module 6. I think we have covered everything. We'll meet in next week class and we'll talk about the remaining topic of the hydrologic analysis.